Hi physics students, this is the solution video for the Unit 5 no friction equation review. This is a review for the test that is going to happen partway through Unit 5 before we learn about friction equations. Alright, number one, before we get into that, here's the equations that you're going to see on that test. Kinematics equations, just in case we need those, and then just that Fine equals mass times acceleration. So, first question, 1,200 kilogram van accelerates from rest to 20 meters per second in 5 seconds. So right away there, it looks like that's kinematics material there. What's the acceleration of the van? Well, I know the initial velocity, the final velocity, and the time, and I want the acceleration. It's going to be this equation right here. I'm going to write down the equation that I'm going to use before I use it, and then put in what I know. And then solve that. Oops. There we go. So 4 meters per second squared is the acceleration. How much unbalanced force is there on the van? Mass of the van is 1,200 times the acceleration is 4. 4,800 newtons. See me writing down that equation there again before I use it. If the van has a total of 3,000 newtons of frictional forces, what's the forward traction force on the van? I'm going to go ahead. It didn't say here in the review to make a force diagram, but I'm going to go ahead and do that. Force of gravity is going to be 12,000. Support force will match that. Got my traction force forward. And friction there. So my unbalanced force equation, I've got traction winning, friction losing. (3,000 newtons of friction force. The mass is 1,200 times 4. If you just went ahead and just put the 4,800 right there, because we already did that, right? So that traction force, adding that over to the other side, must be 7,800, oops, the comma in the wrong place, 7,800 newtons. That's 7,800. All right. That was pretty easy. Hope you thought. Number 2, 70 kilogram person rides an elevator that accelerates downward at 1.2 meters per second squared. So that means if the acceleration is downward, that is the direction of winning. That's the direction of the unbalanced force. So qualitative force diagram of the person, going to be the gravitational force on them, and then the support force from the elevator floor would have to be smaller because I know that down is the winning direction. So what I'd be looking for on the test here is clearly the gravitational force is bigger than support. Unbalanced force equation for the person. A couple different things I'd take as being correct for that. Unbalanced force is equal to the force of gravity minus the support force. That would be fine for that. I would also accept unbalanced force is equal to force of gravity minus support force. So either of those two would be fine, as long as it's got that. That's the key right there, the gravity minus support force. Part C, use your equation from part B to find the support force. So the force of gravity on the person would be their mass times 10. Support force is what I'm looking for. Mass times 1.2. I'm going to do a little bit of algebra there. I'm going to do that off screen. I would add this over to this side and then subtract this over. Actually, I do it on screen for you. So that's 700 minus 70 times 1.2. 616 newtons. Does the person feel heavier, lighter, or the same as usual during this acceleration? Well, if they were just at rest, they would feel 700 newtons of support force. And now they feel 616 newtons of support force. So they feel lighter. Because how heavy we feel is how much support force we feel. Right. Recognize that guy. A 50 kilogram box is pulled across a rough floor. Oop. I should have taken that out. What is this? Because I'm telling you here that there's no friction. So that's misleading to say it's a rough floor and then to say there's no friction. That's my bad. A 50 kilogram box is pulled across a floor by a rope that's 20 degrees above the horizontal. Pulling force has a magnitude of 150 newtons, and assume that there's no friction. So a quantitative, that means with numbers, force diagram, force of gravity would be 500 newtons. And there's going to be a support force. I'm not going to draw that in yet because since this is pulling upward, that's going to change how much support force there is. This is not happening on a ramp, so I'm going to go ahead and draw my X and Y axes in regular like. So here's the 150 newtons pulling force. That's going off into quadrant 2, so I'm going to break that up into its components. Like that. And then I'm going to use my calculator, making sure that I am in degree mode. I am. To find the sine and cosine components. And I like to just do them on the same screen right here, like that. And if I did any kind of decent job drawing that angle in, then it's very obvious which one is which. Of course, sine is opposite over hypotenuse, so whichever way you're thinking about it, this is going to be 141 newtons, and this is going to be 51 newtons. And then the support force is not equal to 500 because gravitational force is going to balance these two up forces, this one and this one. So this would be 449 newtons. How did I get that? 500 has to be the sum of these two. So I just did 500 minus that. You can use your calculator for that, of course. I write the unbalanced force equation and then use it to find A. So in the up-down direction, gravity is being balanced by these two, so nothing happening there. All the action is this way. Unbalanced force is just equal to the the cosine component of the pull. So that's 141 is equal to mass times acceleration It gives me an acceleration of about 2.8 meters per second squared. All right. Number 4, I have an Atwood's machine with 235 grams on one side, 260 grams on the other, kind of like your practicum, a lot like your practicum. Draw force diagrams for each block. So, it's my bigger one and my smaller one. The bigger one, gravity will be winning and tension will be losing. And it didn't say quantitative, so that means I don't have to put numbers in these. And then for the lighter one, tension is winning and gravity is losing. And the tension force, that's what's the same. If I had a nickel for every time I've seen Atwood's machine problems with force diagrams that look like this. Here's gravity, there's the two different gravitational forces, and then that's got to be equal to that, and then that's got to be equal to that. I've seen that many, many times, and that is just not true. If I had a nickel for every time I saw that, I'd have more money than I have right now. Find the acceleration and the tension in the string, show your work. So this is where you have the option of writing the two equations and adding them together or doing the shortcut method. I'm just going to go ahead and do it both ways so that you can see both of those. If you're going to do the two equation method, I think writing the unbalanced force equation underneath each force diagram is probably the best way to go. So here, this one we got unbalanced force is equal to mass times acceleration. I'm using the big M here to be consistent with that. So here, gravity winning, tension losing, force of gravity on the big one. That's 0.26 kilograms. This is 0.235 kilograms. So multiplying that by 10, 2.6. That's what I got for the big one. For the littler one, it's my little m. On this one, tension is winning and gravity is losing. So this 0.235 times 10, 2.35 equal to 0.235 times A. And then for this method, I'm going to add these two equations together. You could rewrite, depending on how this all works for your brain, oops, I put 2.6 there, that should be 0.26, sorry about that. Are you yelling at your screen, telling me I made a mistake? Because that's the mass, right, not the force. So I'm just going to go ahead and add these two. So this side plus this side, I know that the tension forces are going to cancel out. There's my Ft and my minus Ft, and there's 2.6 minus 2.35. You can use your calculator if you want for that. That's 0.25 is equal to, and then I'm going to add 0.26a plus 0.235a. That is 0.495a. And then I will use my calculator for that. That gives me an acceleration of about 0.51 meters per second squared. And, oops, and then also we're supposed to find the tension in the string. I can take that acceleration and go back and plug it into either one of these two equations. So I'm going to go ahead and plug it back into, how about this one? So 2.6 minus that tension force equals 0.26 times 0.51, and doing a little bit of algebra there to add that over here, and then have 2.6 minus 0.26 times 0.51, about 2.47, looks like, newtons. And you can plug the acceleration back into this one too to double check that. I'll go ahead and do that. If I did it in this one, it would have been 2.35 plus 0.235 times the acceleration, and I get 2.47. So whichever one you plug it into, you should get that. And then, as promised, the shortcut method would be if you look at your two force diagrams and you're like, okay, I'm going to just write the total unbalanced force is equal to total mass times acceleration. So total unbalanced force, the tension's going to cancel out, and I have this gravitational force minus this one. So that's big M times 10 minus little m times 10 is equal to the total mass. It's 0.235 plus 0.26 times acceleration, and that just gets me right to the equation here when I added them together. So I'm not going to finish this method because that just turns into this equation. Then everything else is the same from there. All right, last one. A 2 kilogram block is placed in a ramp, angle is 30 degrees. Block is pulled up the ramp by a pulling force, a tension force in this cord of 15 newtons that's parallel to the ramp, and there's no friction. I'll make it qualitative, means you don't have to have numbers. Force diagram. I'm going to try to draw my dotted line that represents the ramp. Oh, look, there's a straight edge right here. I'll try to make it parallel to the ramp. That's going to mean better guessing about what's bigger than what in my force diagram when I have to break the gravity force into components. There it is. Force of gravity would be 20 newtons if you wanted to put that in. Not required here because it says qualitative force diagram. Then I'm going to turn my paper so that that looks horizontal. Make my other axis. And this is coming down into the third quadrant, so break that gravitational force up into its components. I'm going to tilt it back now. The support force, actually, keep it like that for just a sec. Support force, ramps, and such things like that can only support perpendicular to themselves, so that would be like that. And there's no friction, so that's it. Oh no, just kidding. There's this pulling force up the ramp. Forgot about that. And force pull, that is 15 newtons. And didn't say that I need to put numbers in. It's a qualitative diagram, but I still need to label the forces. So that would be that. And I think I'm going to need this information to do the rest of the parts. So I'm going to go ahead and just find the sine and cosine components of that and put them in my diagram. If you didn't do that, if this was a test question and you didn't do that, you wouldn't lose any points for the diagram because it just asks you for a qualitative diagram. So at 20 newtons times the sine of 30 and 20 newtons times the cosine of 30. All right, so that's 10 newtons here, and this is 17.3 newtons. Write the unbalanced force equation for the block. Unbalanced force is, this is winning and this is losing. The support force here is just going to balance that part of the gravitational force. Nothing happening in that direction, no motion. So what is happening is this pulling force is winning, minus the sine component of the force of gravity is losing. And that's equal to mass times acceleration. And to be continued right here, so the pulling force is 15, the sine component of gravity is 10, the mass of the block is 2 times acceleration. Oh, there you go. Oops, is that off screen? There's the rest of it. Bye-bye.